Hi everybody, this video today is going to talk about lesson 1.J in the AP Physics workbook. This is on page 17 of the workbook. I'm choosing to go over this activity because there is potentially a free response question on our test coming up, our quiz coming up, that is very similar to this. It's not exactly the same, but has a lot of the same concepts. So let's go ahead and get started. The scenario is a rocket fires its engines to launch straight up from rest with an upward acceleration of 5 meters per second for 10 seconds. After this time, the engine shuts off and the rocket freely falls straight down back to Earth's surface. Okay, sketch a graph of the acceleration as a function of time from t equals 0 to t equals 10. Okay, so it's firing its engine for the first 10 seconds. It has an acceleration of 5 meters per second squared. Sometimes when people see this problem, they want to take out gravity. This is the actual net acceleration. So that is the acceleration. All we need to do is draw a straight line because that's the acceleration for the entire 10 seconds. And you know what? I should do a straight line. So use your straight edge. I'm going to erase this and do a straight edge. Okay, and then also remember, use a straight edge, but also stop it at 10 because that's the end of the information. We do not want to go farther, and we do not want an arrow. Okay, this next part says sketch a graph of the velocity as a function of time from t equals 0 to t equals 10 seconds. Okay, well, so this was an acceleration time graph. This is a velocity time graph. We have to think about how those are related. This one was 5 meters per second squared. If we have a velocity time graph, the slope of this velocity time graph should be 5 meters per second squared. And so it's going to have a slope, and the slope's going to be up 5 over 1, and we have 10 seconds. So if we go up 5 meters per second every 1 second, okay, that's what that acceleration is. I could also say, well, that's the same as going up 50 meters per second every 10 seconds. Right? It's the same, this just reduces down to this. And it went for 10 seconds. So in other words, I'm going to draw a line. I'm going to use my straight edge again, but I'm going to connect the point from here down to the origin. So again, straight edge. This line goes up 5 over 1, up 5 over 1, up 5 over 1, up 5 over 1, etc. That is my graph. Okay, this next question says, from the graph drawn in part B, so we're using this graph, determine the velocity of the rocket after the initial 10 seconds of travel. Now, we have an equation that we can do for this, but since we already have a graph, it's right here on the graph. At the end of 10 seconds, it is right here. It's 50 meters per second. Another question. From the graph, again, we're looking at the graph, determine the height of the rocket after 10 seconds. Okay, well, we have to think about that. Where's the height going to be coming from? Okay, if we're looking at this graph, the area would be length times width, or base times height, or whatever you want to call it, but it's going to be meters per second over seconds. That is equal to meters. And so that's what we need to do, is we need to find the area of this. Of course, it's a triangle, so we're going to find the area of this triangle. We know that the area of a triangle is 1/2 base times height, so it's going to be 1/2 times 10 times 50. Probably should have put units in there. 10 seconds, 50 meters per second. And we multiply that together, we get 250 meters. So again, we have an equation that we could have done, but it was a heck of a lot easier just to look at the graph. Okay, this next one, you really have to think about the problem. It says, make a claim about the numerical value of the acceleration of the rocket 10.1 seconds after firing, when the rocket engines have been completely shut off. Okay, so this rocket fires up at 5 meters per second squared, and then the rockets turn off. What's going to happen? Well, there are several things that are going to happen, but one thing is, since that acceleration is gone, it still is under acceleration, right? And that acceleration it's still under is 9.8 meters per second squared. Okay, it's going to be under gravity. Gravity's going to take it down, right? So that's the acceleration. Okay, let's go to the next page. Use the definition of free fall to explain your reasoning for your claim in part E. So I'm going to show you what they had in the answer key. And this makes sense. An object that is in free fall moves under the force of gravity only. Therefore, an object in free fall experiences an acceleration due to gravity on Earth of 9.8 meters per second. They call it meters per second per second. That's the same thing, down. And they called it positive because then they said down. If you said negative, that's okay too, because it's down means negative. But free fall is when there's nothing else on it except for gravity. All right, so, like I said, the rocket pushes it up, and then you turn off those engines, and now it's under free fall because gravity is the only thing affecting it at that point. Okay, again, next question we need to think about. 10.1 seconds after the rocket was launched indicate whether the rocket is going to be moving upward or downward. All right, well, again, think about it. This thing gets launched up, and then we turn off the engines. What's going to happen? Is it going to be falling down at that point because it's under gravity, or is it going to be still going up? Okay, you can think of it as like, I don't know about the word floating, but that's kind of the best I can do. It's going to be floating upwards. Like it's still under gravity, so it's slowing down, but it had enough, enough oomph going up, all that acceleration, that when it turns off, it's not just going to fall down immediately. It's going to keep floating up for a little bit longer. Okay, it says choose one piece of evidence to support your claim and write it below. Let's go back to our graphs and see what they can do for us. The evidence that we need is from our graphs. Well, one thing is on our velocity time graph, after the engines shut off, it's going 50 meters per second. It's not just going to automatically stop after 50 meters per second. It's going to slow down due to gravity, but it's not just going to stop immediately. And so that's what I'm talking about. It's going to be kind of slowing down a little bit. So I would choose this graph as my bit of evidence. And so they went into some detail here. But if they say if it's going 50 meters per second, which we just looked at, with the rockets turned off and the only force of gravity is exerted on the rocket, making the acceleration negative 9.8 meters per second squared, it will take an additional 5 seconds after the rocket turns off for the rocket to come to rest. Meaning that for time between t and equals 10 and 15 seconds, the rocket will continue to move upward. Let's just talk for a second about, so they use negative 9.8, which is fine, but a lot of times in AP world, we use negative 10 meters per second squared because it just makes sense. So that means that it's losing 10 meters per second. I'm going to write that the way they had it because it's going to make some sense to us. It's losing 10 meters per second every second. And so if it started at 50 meters per second, that's where it starts. And then after 1 second, it's going to be going 40 meters per second. And then after 2 seconds, it's down to 30 meters per second, and so forth. And so that's going to take it 5 seconds. And at 5 seconds, it's going to be 0 meters per second because it's losing 10 meters per second every second. That's where they got this 15 and this 5 seconds. Okay, this question continues on the next 2 pages. So let's go ahead and move on to the next 2 pages.